So my presentation will be about the identification of linear vegetation elements in rural landscapes using LiDAR point clouds. And yeah, for that we're also going to use a bit of machine learning. It's not only about machine learning, but we're definitely going to use it. So what are linear elements? Well, over the years agricultural practices have created a mosaic landscapes where linear elements have divided up the landscapes into patches. These linear elements are things like roads, tree lines, hedges, and waterways. And these elements have an important function in the local ecosystem because they function as corridors and barriers for fluxes like animals, plants, water, nutrients, and are therefore important in quantifying the health of the ecosystem in these landscapes. So in previous research we actually thought of this project because we ran into a paper that tried to map these elements using interpolation between ground points. So over the whole Europe, they took points and just counted how many elements do I see, and then interpolated between all the points. Of course, and you do a lot of assumptions about where linear elements are. And if there's linear elements here, then there must be half the linear elements between two points, for example. And that's just a lot of assumption. We thought that can be done way better. We'll use remote sensing to actually detect the linear elements and then make a map that way. Because more and more nations are having nationwide LiDAR data sets freely openly available, and LiDAR data is very suitable for detecting vegetation, we decided to use LiDAR data. So I don't know if everyone knows what LiDAR data is, but LiDAR data is you have a laser scanner under a plane, it shoots a laser down, and depending on how long it takes for the laser to come back, you have a height measurement. So you get a 3D scan, as you see below, of the landscape. So how do people classify LiDAR data sets? There are basically two main strategies. You can derive raster products from the LiDAR data, or you can classify the point cloud directly. Of course, if you make a raster from a LiDAR data set, you use a lot of information. You basically flatten the whole thing, and you lose all your 3D information. So we wanted to use the point cloud directly, and then use a machine learning algorithm to classify each point. In detecting linear elements, what you often see in research is that it's raster based, and it's mainly used to detect roads. And there you kind of use the properties of the roads to do assumptions in your methodology. So these algorithms I found weren't really useful for what I wanted to do. So I had to think of my own. So my aim was to develop a method to delineate these linear vegetation elements in LiDAR point clouds. And I wanted to basically answer the questions like, what are the characteristic LiDAR features of vegetation? Can we separate linear elements from non-linear elements, and how accurately can we classify and segment linear elements from non-linear elements? So my research area, I chose my research area because to have a variety of linear and non-linear elements that were of different kinds of shapes, curved, straight, and that were attached to non-linear elements or were isolated, and all these kinds of different things, a very heterogeneous area, to ensure that both the classification and the delineation of linear elements could be efficiently trained and tested. So this was the area I chose. It's in Gelderland, in the center of the Netherlands, and as you can see, there's a lot of different tree lines and hedges and all that kind of stuff. So the data, we use the AHN3 data rather than the already nationwide AHN2 data. But the AHN3 data has information on multiple returns. And multiple returns is when you send out a laser and it partly hits an object, but it goes on. And one signal already comes back, and then the signal goes on and hits another the ground, for example, and then also comes back. So from one laser pulse you get multiple laser returns, and that often happens when you scan vegetation. So it's a very useful feature to have when you're classifying vegetation. So my method, I'm not expecting you to analyze this whole workflow, but what I want you to see is that there are 3 basic steps: the feature extraction, the vegetation classification, and then the linear object segmentation. So the feature extraction, to get extra information on each point, we for each point defined a neighborhood using k nearest neighbors. And then in each neighborhood, we can compute some basic features, so like the height difference within a neighborhood, the standard deviation of the height within a neighborhood, the radius of the neighborhood, and the point density within the neighborhood. But we can also, to say more about the relation between the point and its neighborhood, we can also compute extra features based on the structure tensor. The structure tensor is a way to describe how a point is lying in its neighborhood. So to do this, we first determine the predominant directions of a set of points, and we do this by computing the eigenvectors and eigenvalues of the covariance matrix. So and then the eigenvectors basically say in what direction the points are in, and the eigenvalues the magnitude. So what you can see, if the points are spread out very much in a line, then the first eigenvector is like that, and then the eigenvalue will be very high, and then for the second it's smaller, so the eigenvalue will be less. So these, with the eigenvalues, you can basically quantify the distribution of the points in space. So if you can imagine if the first eigenvalue is way bigger than the 2 after it, it's very linear. So almost all the spread is in one direction. If the first 2 eigenvalues are very big and the third is very small, then it's very flat, very planar. And if the 3 directions are all basically the same, then the points are very spread out in space. So
I like your hints.
I hope that's a bit clear. And these properties are basically summarized in a set of equations, and then we come to this complete feature set, which the first is purely based on the points and the return information, then the 4 basic geometric features, and then 8 eigenvalue based features. So then we do the classification, and first we can already throw away a very large portion of the point cloud, because in vegetation always results in a very scattered neighborhood, so without using any machine learning, we can just based on the scattered information, we can already throw out a lot of points, which will decrease the computation time further on in the workflow. So then we do a super...
Can I ask something?
Yeah.
You said that waterways were also point of interest, and those are not vegetation. I mean, that's as far
right.
as you
So
can get it.
the roads, waterways, also very interesting topics, but I focused on vegetation only, just to scope my research. I mean, you could also do it again, maybe with a bit of a different methodology, but just for waterways or just for roads. But I focused on vegetation. I'm sorry I didn't mention that. Yeah, my focus is only the vegetation, and also only the basically the higher than herb vegetation. So grasses and stuff I see as non-vegetation. Well, of course it's vegetation, but it's flat.
That's my God. I wish.
Yeah. So yeah, we do supervised classification, but we have to notice that we now got a very imbalanced data set. So because we threw out all these points, almost all the points we are left with are vegetation, and only very few are not vegetation, but we still want to filter those few out. But if you use normal classifiers, this can lead to a problem, because a classifier can just call everything vegetation, and will already achieve like 95% accuracy, for example. So you need to come up with a bit of a strategy to handle this problem. So you can, for example, upsample or downsample the minority class or downsample the majority class. But with the random forest, what I used, you can kind of do something a bit smarter, I would say. I don't know if it's actually smarter. I thought it was smarter. And that is because you're already taking subsamples every time you create a decision tree in a random forest. You can, instead of doing the normal random subsampling, you can each time take a bootstrap sample of the minority class and then just take a random sample from the majority class based on the size of the minority class. So then each time you're using different type of data from the majority class, but keeping the both classes you're keeping balanced. So in that way we want to remove the bias towards the majority class. So to assess the accuracy of the classification, I did a manual classification based on the point cloud, the area imagery, and a ground survey. I did a 10-fold cross-validation, and then again we have to think again about the imbalance, because it is so imbalanced, the normal metrics are not really useful. Because if you're going to look, we'll see later, and I can explain later why that is. But the ones I found in literature that are useful for imbalanced data sets were the area under the ROC curve, which tells a bit about how well the two classes can be separated. The Matthews correlation coefficient, which says something about the correlation between the predicted classes and the observed classes, and a geometric mean, which is the mean between the producers' accuracies of the two classes. Then after the classification we're going to segment, and I basically thought of an algorithm to do a region growing and add points as long as the region is still rectangular. And if we have a rectangular region, we can see it by the length and the width if it's linear. But first we do some pre-processing step, because linearity is only a two-dimensional thing. We don't need the height to determine if something is linear. I removed the height information, and I downsampled a bit to decrease the computation time. Of course, this leads to a bit of loss in precision, but it was really needed to keep the computation time low. But you can see in the picture that even with the downsampling, I would say the accuracy is still quite good. So what is rectangularity? The rectangularity is defined as the area of an object divided by the area of the minimum bounding rectangle. So we need to find both these areas. So the area, so the minimum bounding rectangle can be found with an algorithm called rotating calipers, which basically you rotate the system by the edges of the convex hull, and it is defined that the bounding box has an edge that is equal to one of the edges of the convex hull. So if you rotate by the edges of the convex hull and look what's the min and max x and y in this system, then at some point you find the minimum, and that will be the minimum bounding box. And then you need to find the area of the object, and I did that by computing a concave hull, specifically an alpha shape. And you get an alpha shape by doing a triangulation of the points and then removing the bigger triangles. So the triangles with a circumradius of larger than 1 over alpha, where alpha is a parameter that basically decides how precise the thing is. So yeah, the shape is. So it will get very. Here you see it's quite how do you call that?
It really hugs it.
Yeah, exactly. And if you increase the alpha, then it will be more smooth. And then we're doing this region growing thing. So we take the green points here are the starting neighborhood, the start region, and then we take a point, we look at its neighbors, those are the blue stars, and of those neighbors 3 points are outside the neighborhood, so those are the points we're going to check. So we're going to check a point by adding the point to the neighborhood, then checking the concave hill and the bounding box with the point added, and if it's still below the threshold of rectangularity, then the point is added to the region and this whole thing is continued. So this will continue to grow as long as the region is rectangular. And then because the resulting regions are still a bit fragmented, I also merge certain regions that are close to each other, facing the same direction and align. And after the merging, I compute the elongatedness by dividing the length by the width. And here we check the accuracy by, I converted all the vegetation points to a polygon using an alpha shape, and then manually cut the resulting polygon into linear and non-linear. But we have to keep in mind that it is quite arbitrary when something is linear and non-linear. It's very much based on interpretation. When do you think something is linear, when not? So there is definitely some arbitrariness in there. And then, and it also evaluates the accuracy of the segmentation, given that the vegetation points you give it were already accurate. So this accuracy assessment only assesses the accuracy of the segmentation. So the results. This was the result of the classification. Here, gray are the points that were removed based on the scatter. Blue are the points that were classified as not being vegetation, and green being vegetation. And to me, this looked quite good. So a lot of the blue lines you see are small ditches. And here you see some farms that have been removed. And other than that, all the vegetation seems to be classified well. So if you look at the numbers, we can see that the vegetation is classified very well. If you compare the number of the true positives against the false positives and the false negatives. But the accuracy of the other class is less well. I mean, if you look at the difference between these and these, there's a way less difference. But here you also have to keep in mind again that we have a very imbalanced data set. So a very small percentage of the vegetation being classified as other already results in a very impacts the ratio of these two by a lot. So it's actually giving a kind of a wrong idea about how well the other class was classified. If you look at the metrics we used, you see the area under the ROC curve very high with a 0.98, which means that according to that metric the classes were separated really well. The Matthews correlation coefficient is also high, shows a high correlation between the observed and the predicted classes. And the geometric mean is also high with a 0.9, where of course the vegetation class was way higher than the other class. So if you look at the delineation, on the left we see the automated delineation, and on the right you see my manual delineation. And you can, at least I thought this looked quite good. You see, of course, there are errors. For example, if you look here, you see that you would ideally you would cut off this point here and here, but because the algorithm continues to grow a bit and only here it comes below the threshold, then it cuts it off here. So there, of course, there are some errors like that. Other errors you see are, for example, here you see that because I didn't classify this as a linear element because I saw this patch, forest patch was way bigger than it is, but here you have an edge case, so there it doesn't go well. And here you also see a bit of red where here it is green, and this was because these are rows of trees that go like this. So these are linear like this, but they don't get merged because they're not facing the same direction. So that's why you get a big patch that's not linear. So there are definitely some errors, but overall I would say, based on these pictures, I could quantitatively say quite well. Here I made a map of how the true positives and the true negatives look against the false positives and the false negatives. So you can basically see what I already told you before. But you see a lot more green than red, so I was quite happy with that. In more numbers, so here we're comparing the area of the predicted and the actual, and again you see that the area of the true positives and the true negatives is way bigger than the false. This shows an overall accuracy of 0.9, a Matthews correlation coefficient of, again, by coincidence, the same as before, 0.76, and an F1 score of 0.82, with also good, at least very good users and producers accuracies for both the classes. So the discussion on the classification. I didn't have a validation data set, so I only used this one research area. This was mainly because of time constraints, so this would definitely be something I would like to still do, to validate this on a completely different data set. The other accuracy not very high, but again we have to keep in mind the removal of the points. Also because the points we threw away are very easily classified as non-vegetation or other. Those are the easiest points to classify, and we threw them all out. So of course you're left with the harder points, and that leads to less high accuracy numbers. Other possible improvements, we could look at the importance of different features and throw out features that are maybe not adding a lot or even making it worse. We could try different ways to handle the imbalanced data problem, like upsampling or downsampling in some smart way, or use different machine learning algorithms. Just like before, I used a random forest. There are a lot of them, so maybe a different one would give a better result. But we have to remember the purpose. My purpose was not to achieve the best classification, but to delineate the vegetation elements. And what you see is that the misclassified points are spread out basically evenly throughout the whole area. So they didn't impact the subsequent delineation of elements at all. And the identification of linear objects, there are some inaccuracies, as you saw, but I still think it went rather well. We have to note, of course, that the linearity is quite arbitrary. I mean, when is something linear, when is something not? It's just not set in literature. There's no real rules for it, so it's just very difficult to really do a very good accuracy assessment. The main drawbacks for me are the computation time for this area took like half an hour, a bit more, just to segment the area. Of course, it could be faster. The merging is not always correct. I mean, what I said before, because these trees are in this pattern of being two trees, then you get segments like this, and then it doesn't merge them because the direction is all facing downward and it doesn't merge. So if you could find some better way of still merging those, that would definitely be a improvement. But it was successful in delineating the majority of the linear elements. So,
Can I ask?
yeah.
I missed, well, firstly half of it, so I may ask something very stupid, but if you use a layer of roads or waterways, would that help in, I don't know, if you could include it in somehow as sort of like, oh, this is a boundary, or this is a line, or this is, you use the extra information.
Right.
Because vegetation usually follows patterns of other
Right.
layers.
I could imagine that that could improve the result. For me, it was I wanted to just use this one data set and not, because we wanted to do this on a European scale. So if you're dealing with multiple nations, then the data sets you have available can differ very widely.
Yeah. But OpenStreetMap.
Yeah, the roads would be
True,
good.
the roads would be
Better than your linear features.
true. That might lead to an improvement. I chose to use just this one data set to make it as generally applicable as possible. Not all linear features do follow roads, of course, but yeah, it could definitely help. Yeah, and now the idea is actually, of course, to scale this up, because the ecological value will only become apparent when this is upscaled, and then it can serve as an extra indicator for ecosystem health and biodiversity, and maybe a similar kind of algorithm could also be used to automatically detect roads, ditches. I don't know. I haven't tried it, but maybe. So that was my presentation.
So are there any questions still remaining?
I have one. Did you check into computer vision? What they seem to have a lot of already invented methods to find lines in pictures.
Yeah, like the U transform. That's true. But those methods are always based on making it a raster. I wanted to try not to do that, but I haven't actually tried any of the methods. I tried the U transform a bit. I didn't achieve success with it, but that was probably because of my incompetence and not because of the U transform. But no, that's definitely true. There are also in computer vision methods to see linear features.
Have you considered, continuing on the computer vision note, modeling it not as a line drawing problem but as a segmentation problem? So not so much finding the lines but finding the patches that the lines delineate? Because if you rasterize this and treat it as a computer vision problem, it's basically an image segmentation problem.
Right, yeah.
And the lines follow from the patches. Although it might be more difficult to do with from the sort of point cloud perspective.
I'm not entirely sure what you mean, the lines follow the patches.
So I mean, what you're doing now is you're trying to find the lines that separate two bits of land or two. So what you could also do, especially with a raster image, is just try to find the picture where the bits of land are colored.
Right.
And then make that your. That would then be essentially your accuracy or your loss function.
Alright.
How many of these pixels have you colored correctly?
Okay.
Which is close to what you have here, except that you want to enforce this linearity, I suppose. So you want to enforce that the segments are linear. I guess that's the problem.
And would that only, if you're going to scale up, right, European level?
Well, that was the idea. My project is now
Just give it
done.
Is that scale up?
Well, if the ceiling is a half an hour per patch, then yes. Within that, we can work within that. So there's lots of stuff you can do. And I think ideally, probably the ideal solution would be multimodal. So you use both the satellite image and the point cloud, and somehow you put them together. but that would also be quite complicated. So I don't know if this is now your PhD
No,
project or if this is something you're not allowed to work on anymore.
No, this has been done for me.
Okay.
You could maybe also look at extension of convolutional networks to 3D images, so the tensors indeed. For example, for MRI studies. So perhaps that could be used in a similar fashion in this case. So if you perhaps have enough of these manually delineated images or point clouds, you could try that.
Yeah. Yeah.
All right.
Also,
Oh, yeah.
one question, because that's the methodology for rural areas. Do you think that that's applicable also for cities?
A good question. Yeah, I think so. Because the classification of vegetation remains fairly the same. You see buildings are quite easily separated from vegetation because buildings always result in just one pulse back and are also very planar and instead of the scatter of the vegetation. So I think the classification should work just fine. The delineation of linear elements might go worse because more often I think in urban areas the trees are separated a bit more. Might not be the case actually, I don't know. But that could make it worse because if the trees are separated then it's harder to make it a line. Yeah. I
Okay.
haven't tried it.
Okay. Thank you, Chris. Thank you, Sanne, for the really interesting presentations. Thank you for being here. I think that there's some other groups that are going to discuss other things at the moment, so we're just going to leave it like this. To the Unigis students who will be listening to this video, we will create more videos like this so we can share our research with you. So thank you for watching, thank you for being here, and see you next time.